Now, one important also facet to this is to think about how we have perpendicular vectors. Perpendicular vectors are going to be something important in several different places. And my first point here to you is to note that they're also called orthogonal vectors then. So they'll use those two simultaneous, not simultaneous, but synonymous, either or. It turns out that for perpendicular vectors, your dot product is going to be 0. All right, we know that with perpendicular angles, then our theta angle between is going to be pi over 2 or 90. And then the dot product, let's say it's A dot B, is 0. Why? A and B are orthogonal. The dot product is 0. Why is that? What did you say? I'm sorry.
Well, I was
Aha. Cosine of pi over 2 is what? Is 0, yeah. And so if our angle is 0, you know, we've got the dot product. One way of thinking is it's the magnitude of A, magnitude of B times cosine of theta. Well, if the theta is pi over 2, the cosine of that pi over 2 is 0. And so, yeah. So that's why for perpendicular vectors, we're going to have the dot product is going to be 0. All right. So let's show that A equals 2i plus 2j minus k is orthogonal to B 5i minus 4j plus 2k. I guess there's a couple ways we could do it. We could show the angle between them is pi over 2, but there's an easier way, isn't there? Yeah, use the dot product and the original version of the dot product, A1, B1 plus, yeah, let's see what that dot product is. 2 times 5 would be 10. 2 times minus 4 would be minus 8. Negative 1 times 2 is negative 2. How about that? 0. Very simple calculation for that one. So since the dot product is 0, these are orthogonal. All right. Now, something else, just kind of showing some different things that might be helpful here to know about the dot product. Another thing that we can utilize dot product for is to project one vector onto another, and that's something, I don't know, maybe you did something like that in physics, but sometimes is a good thing to know how to do. Okay. So let's talk about the projection, and we'll do B onto A. Do it the other way. We'll do, the book does it with B onto A. And here's, let's say A is here, and then B is here. And so what geometrically we're talking about with projection is kind of the book also says, well, it's kind of the shadow that B would be to A. And what you do is you just drop down a perpendicular to A, and this amount right here, that would be the projection vector of B onto A, we'll call it. Okay, yeah, it's definitely tied into that dot product formula. Yeah, here's going back to our definition. Well, we can see here that our magnitude is, since that's angle theta there, the magnitude of this projection vector magnitude of that would just be well, the cosine of the angle is the projection length, the length of that projection vector, divided by the length of B, magnitude of B. And so the length of the projection vector would just be, wouldn't it? Magnitude of B times the cosine of theta. Yeah, cross multiply there. Okay. Now, if we go up here to this, then if we get the same thing, solve for the same thing here, B, magnitude of B cosine theta, or I guess we could just substitute this then for that. In terms of, all right, so this is equivalent to that, and so we've got the A dot B is equal to the magnitude of A times the projection length. Notice this. The projection length, in just turn, instead of having to get the cosine or anything of that angle, all we've got here to do is take the dot product and divide that by the magnitude of A, don't we? All right, and the book refers to this as the component part of B projected onto A. That's what the book will refer to it as, but it's just the magnitude. It's just the magnitude of the projection. Okay. Now, this forgot to draw it in, but it is a vector. When we're talking about a projection of B onto A, we're talking about a vector, and this just happens to be the length of the vector right there. Now, how do we get then? Because on a vector you need length and you need direction, and so the direction. Well, the direction. We're just going to use the unit vector, a vector of unit 1 length, and remember we talked about that. This. So our component or part of B projected onto A is A dot B magnitude of A. All right, and so what we're going to do is we're going to put this projection is in the direction of A, and we're going to utilize our unit vector. Remember, it's 1 unit long, but in the direction, same direction of A. Remember what it was? Yeah. You just take the vector and divide it by its magnitude, and that unitizes it, as we said. I don't know, that's not a mathematical term there, but you know what I mean. All right, and so what we do then to actually get the projection vector itself is we're going to multiply these two together. We're going to take the length of the vector and the unit the direction is, we're going to use the unit vector here, so we're going to take the component part times the unit vector to get our direction. And so that will take a scalar times a vector, and so that defines the actual vector, projection vector. Now, there's different forms you can write. If we combine these, then we get the magnitude squared on the bottom times a. But in practicality, as you work these out, this is if you want both parts, get this part and then just multiply it by the unit vector. All right. And so here's what type of question they'll ask. Find the scalar and vector projection question. Now this is just going to be a scalar here, a scalar amount. Yeah. So it's not going to be the b vector is not going to come out of that at all. All right. Find the scalar and vector projection of vector b 6, 5 onto vector a 3, -2. All right. Sorry. All right, so the scalar part of the projection is just this. That's our scalar. It's the component part of the projection. And it's just the dot product over the magnitude of a. Dot product, 18 minus 10. Magnitude of a would be the square root of 36. Oh, that's going to work out nicely. So we've got 8 over 6, 4 over 3. Did I do something?
I was wrong.
Oh, okay.
I don't think it's square root of 36.
9 plus 4. Oh, not square root of 36. I multiplied those, didn't I? Square root of... Okay. Okay. How about square root of 13? Is that better? All right. 8 over the square root of 13. And so that's the length of that projection. The actual projection, the vector projection, would then take that, the component, 8 square root of 13, times the vector a divided by the magnitude again. And so that would be 8 over square root of 13 times vector a, which is 3, -2. And then the length of a again is square root of 13. And of course, yeah, those two are going to make just 13, aren't they? And probably the way they would write it then is just distribute, if you will, distribute that in. So the vector would be 24 over 13. You take that times that. And then the second component would be, -16 over 13. Okay?